All right, everybody. Welcome back. Um, so this last session of today is going to be a little bit lighter. I'm going to talk a little bit about some of the emerging methods that are coming out and my thoughts on those. These advanced sessions will get heavier as we go on and we get into quantum error correction and optimization and things like that. But I just wanted to take a moment to take a look at some of the emerging methods and stuff. Um, I'm going to post after this a reminder to everyone to register for the hackathon if they have any interest in participating. I highly recommend you do. And please feel free to reach out to friends or anybody you think might get value out of this. Let them know that, like, hey, you can just go check out the videos and stuff like that. But, put the stuff together. I'd love for people to be able to take advantage of it. All right. So let's talk about emerging methods. So sample-based quantum diagonalization and sample-based Krylov quantum diagonalization are these newer methods for trying to approximate the ground state of a system. For any system that you can represent as a matrix, whether that's molecules or graphs or what have you, a lot of times by evaluating the spectrum of that system, you can understand key components of how that system works. For molecules, you have a ground state where when none of the electrons are excited, how much energy that molecule has. And I'm kind of simplifying here a little bit because there's notebooks that I'm providing that do a better job of explaining it. But if you can understand the ground state energy of that system, you can better predict how it will interact with another molecule, how it will behave in material sciences. For graphs, if you understand the spectra, you can approximate things like centrality and connectivity. It's a huge potential, and this is something that's really surged to the front this year. It's a class of algorithms because you have variational quantum eigensolvers and you have these quantum diagonalization methods that are all trying to approximate the spectrum of a system. And they're very, very interesting, and it's something that's really showing the potential for quantum advantage here. So you have the Hamiltonian. Now, a Hamiltonian, for anybody who's not familiar, is, a matrix. It's the state of the system. It's oftentimes represented by a quantum circuit that encodes features, from whatever system you're looking at. So you prepare your quantum state, you encode, whatever features you need to into your quantum circuit, and then you're going to do sample measurements, and then you'll diagonalize classically. And so this is another one of these hybrid algorithms where we're passing back and forth from quantum circuits to be able to handle complex mathematical aspects, and then trying to optimize these circuits based on these sampled measurements. So instead of measuring every single thing, we sample and optimize and iterate, and it's shown that it's really good about being more noise tolerant. It's pretty efficient for large matrices, but it avoids the full diagonalization of the matrix. So it's still an approximate method, but it is showing that it's showing some improvement. It's showing some people getting excited. People are using these methods to predict how proteins fold, to understand how molecules interact with each other, to try to understand various things like this. And so the sample Krylov space version is using something from linear algebra called a Krylov subspace to sample these excited energies. If you're familiar with the kernel trick, it's analogous where you project something into a different dimensional space and you're able to separate or better understand things by doing that projection. So you generate your basis states with quantum, and then you're going to sample the overlaps in this Krylov space and then do your diagonalization, your optimization. Okay, it's mathematically provable convergence, still very resilient to noise, and like I talked earlier about variational quantum eigensolvers, it's been outperforming those in convergence and speed and accuracy. lattice gauge theories, which I honestly don't understand that well. It's been applied to, it's been doing well. It's been demoed on, molecular energies. A nitrogen molecule is a great little test bed that you can fit on a quantum circuit and run for yourself. I'm pretty sure I've provided a lab for that, but also we have an entire day where we're going over sample-based Krylov quantum diagonalization in the advanced sessions.
Should we be able to see your screen?
Yeah, you should. I am so sorry.
Sorry
Share.
for interrupting.
No,
I had to
please.
set up push talk.
No, yeah, that's awesome. Thank you very much. All right, can everybody see it now? Somebody give me a thumbs up or something. All right, cool. All right. You guys got to hear me verbally talk about it and try to picture it in your mind, which I appreciate y'all working with me through. But sample-based quantum diagonalization and Krylov space diagonalization are emerging methods that are out-competing the variational quantum algorithms that have been, part of the milieu for how quantum computing works for the last 5 or 6 years. They're showing that by sampling the state space and projecting into a Krylov subspace, that we're better able to try to approximate the spectra of these states, whether that's molecules or lattice gauge theory. They're showing a lot of promise. We do have a day in the advanced section, I think it might be this weekend, where I'm going to go over that and walk through that lab. Wire cutting and circuit knitting. This is getting interesting because, quantum computing offers true parallelism. We can evaluate many states at once. However, we are still very limited by our circuit size and coherence times. We only have so many qubits and we can only do so many operations, before that noise gets introduced and we have to add error correction. It gets harder and harder. Circuit cutting and knitting is interesting because what we're doing is we're taking these large quantum circuits and cutting them up and then running the outputs from them on tensor networks, or passing the information back and forth between quantum circuits. So we're trying to approximate what we could do if we had an ideal large quantum circuit, okay, but trying to find out how we can decompose this large quantum circuit to fit it on a variety of different processors and knit it back together with, classical methods, tensor networks. It's, and there's the aspect of like, okay, surpassing, let's say, we have a 130 qubit Heron system available to us through IBM, and so sure, we could use that to, surpass that. But also, as we iterate, there's a lot of smaller systems out there that are available, whether from IBM or from someone else. And it's like, okay, so, quantum computation, I only get 10 minutes per month on this class of systems, but if I can access these 10, 20 qubit systems, perhaps I can bypass some cost or some wait time or, some expense by knitting my circuit among smaller devices. It's really useful for these variational algorithms things where we are constantly parameterizing and updating the parameters on these relatively small circuits, and we can spread it out between these quantum devices instead of trying to fit it on one. Quantum echoes. I've just been reading about this. I mean, I heard about the press release earlier this year that Google had a 5-minute computation on something that is just indescribably long, septillion years or something. It's a time span where most of the stars we see in the sky have burned out. So it's basically they set up the state, all right, and they apply these time evolution operators that apply rotations and amplitude changes to the quantum state and start sampling the correlations. So they're trying to apply these time operators where at intervals they apply these gate operations to the quantum state, and they're kind of seeing the emergence of a correlation over time, a wave almost. Um, it's proves practical advantage. I haven't dove into this a lot. I don't know a lot about this, but that 5 minutes versus septillion years is just a kind of insane claim, and it's just one of the true quantum superiority examples that we've seen. It's encouraging to me because there's others out there. We're going to continue to find these quantum superiority cases. It is something I'd like to dig into a lot and very soon. But this quantum echoes algorithm is just interesting with that insane speed up. All right, this is in my wheelhouse. So group theory, for anyone who's not familiar, is used a lot in any combinatorics type of situation. How many different ways can you combine these things? Oftentimes you end up with symmetries when deciding how to combine things. If you're trying to define the structure of a highly regular graph, you'll have many subgraphs within that graph that are isomorphic or that can be connected without changing the overall structure of the graph. And so group theory is basically cutting whatever you're working with up into these symmetrical elements to where you can, permute them and treat them as a thing. And it's another way of bypassing those factorial types of combinations. It's dynamic programming in a way, where we identify symmetries that we don't have to recalculate things that we already have. This group theory algorithm providing an exponential speed up in symmetric systems. Now, that depends on how symmetric your system is, but they've applied it to molecular simulations, which makes a lot of sense. Molecules have a lot of symmetry, both in the fields they have around them and in their properties. There's a lot of interesting applications for being able to apply these group theory transformations to systems. It's the hardest problems that we can come up with for classical computing are these factorial and exponential type problems that combinatorics offers up so much. The Baskin-Robbins, there's 31 million different combinations of their toppings. That exists everywhere, and that's a big thing that drove the development of machine learning, is that, okay, it's not possible to actually calculate this. Let's do some gradient descent and try to get to a good answer, because the space is too big to actually explore. And so there's these steps like this group theory algorithm that move us towards actually fully exploring the space, or at the very least drastically increase the amount of the space we're able to explore with our heuristic algorithms. Hardware-based quantum error decoder. Okay, so quantum error correction is a system where we use more than one qubit as a logical qubit. So perhaps we have 7 or 12 physical qubits that are operating as a logical qubit, because we're using the interference between these qubits to make sure that if a qubit flips from a 0 to a 1 or 1 to a 0, or its amplitude or phase changes, the other qubits reinforce it and force it back into the state it was. It's really expensive, not only on the qubit count, but also on the logic side count of it. Okay, great. We now have 12 qubits operating as one, but our circuit is now so much deeper to provide for this error correction. Okay, but by having a hardware-based quantum error decoder, where instead of us applying these gate operations, this hardware is designed with this error correction in mind for these qubits to work together to reduce their error rate. It's another step towards that fault-tolerant quantum computing, where right now it's so often we're worried about how deep our circuit is, how many operations we do, because we know that if we run the circuit for too long, it just devolves into noise. All right. Otherwise, you need error correction. And so this hardware base, where we're not adding tons of gates and, software side error correction, but that it's baked into the hardware is an interesting development. So, like, that's the news on what I think are, like, some of the most interesting things out of the last year or so. I would like to point out to everyone that here is stop streaming and stream. Where am I at? Sure. All right. So that in the text channels I have this ready to go hackathon ideas. Okay. And there's some that are kind of vague, grab bag or project ideas. There's some that are a little bit more focused. I have a really beginner friendly number generator here. You know, a common thing that a lot of people don't realize. You know, anybody who does machine learning uses numpy.random or random.random constantly, but it's not actually random. You know, it's modulo arithmetic a lot of times, or other various methods, or, you know, they'll sample the clock for getting a pseudo-random number. But quantum computing actually allows a method for having a truly random number generator. You know, and it's not necessarily the most complex, but it would potentially solve, you know, the unseen biases that come from these number generators that aren't truly random. I have the sample-based quantum diagonalization for chemistry, and I have lots of other resources on that. There's options pricing using quantum computing. There's a quantum minesweeper that has to do with how quantum can be able to infer the existence of things without actually measuring them. It's quantum key distribution. And then also, I'd like to point out that in the state of the art in quantum computing, I uploaded like 6 notebooks here. These are all pretty advanced, but most of these were taken off of the tutorials page on the IBM Quantum Learning platform, which I kind of want to show off.